GR12 probability, we are busy finding out in how many ways stuff, objects can be arranged. Now we're looking at the number of arrangements if there are things that are identical. So if you had any three objects, doesn't matter what they are, but they were not the same, in how many ways can you then arrange them? Three of them would be three. Factorial, which means 6 ways. Right, but now, whether I write I like it is, or there, or what did I do? Yeah, like whatever, yeah. How many ways are there? How come? Because whether you swap those two around there, or swap those two around there, or swap those two around there, it doesn't make another arrangement because they are identical. So we're going to get to textbooks typical. If you have all of your textbooks here and I put them all on one heap, how many ways can they be arranged? One. Because they all look the same. Are you with me? But if I say I've got 5 different math textbooks, how many ways can I arrange them? 5 factorial. Are you with me? That's where we're getting. So with I, you can see it's 3 ways, and if you sorted that out in your mind and you said to me there are 3 permutations or 3 type of arrangements, that would be that. But now you have to be taught the way. How many ways or how many arrangements? Being taught, that is what you had, 3 factorial, which is wrong, you know that, because that's 6. 3 times 2 times 1, that's 3 factorial. But then you have to divide it by all of the number of repetitions if you want to. Okay, that's very unmathematically put. So if you say 3 factorial, and you look at, for instance, the E, there are 2 of them. The Y, there's only one. Now, you can write that there, you don't have to write that there, but if you do, you also understand that you're checking everything. For the E's, there are 2, for the Y's, there's just 1. So what happens there? You've got 3 factorial over, okay, well, 1 factorial is 1. What happened here? You've got 3 ways. Now guys, you didn't have to do that. If you could just figure it out in your mind, you wrote me the answer of 3, you would get your 2, maybe 3 marks. That's it. So let's have a look at another example. Deed. First thing that you would say is the number of arrangements or the number of permutations is 4 factorial. But then you must remember they are identical, because they are identical. That you would be dividing the D's, there are 2. And the E's, there are 2. And then that's it, because you're not going to repeat that again. Are you with me? Does that all cancel out and that's just 1? Remember what 4 factorial is? And what is 2 factorial?
2 times 1.
Which is not all cancelling out. Be careful. Still getting to know the whole factorial thing. What is that then? If you want. How many ways?
6.
Can you punch that into your calculator with the factorial, see if it's 6? Yes. Okay, happy on that? That's the ball game. Now, next example. If I show you the letters M-I-S-T. Okay, now remember here, please, it doesn't have to make sense. It's just arranging them. It's like your little brother sitting there with 4 little blocks, and he has to put them in a row. There's no sense of this must make a word or anything like that. Are you with me? Because this doesn't make any sense. Maybe he, ha, I don't know, but it's not sense. Any way is possible. So first of all, how many ways?
4 factorial.
Okay, now guys, if you wrote exactly what I wrote there, now the guys will give you your full marks. I don't like the way that the probability is always written. I would like you to say number of arrangements. That's just me. Can you leave it in 4 factorial? Yeah, you're allowed to. What is the actual answer? 4 times 3 times 2 times 1, or just put it in the calculator. How much is that? 24 ways that you can put those 4 little blocks differently. 24 ways. No repetitions. If you really wanted to do that, you had to actually say there's one M, there's one I, there's one S, there's one T. Ma'am, that's stupid. Yeah, I hear you. But let's keep it all together. Now the question says, next one. If you have the I changed into an S, if the I is changed into an S, do you agree? Yeah, now this would be better if I just gave you this and said how many repetitions. So first of all, the number of arrangements is 4 factorial over, let's humor ma'am. This would be 1 factorial, this would be 2 factorial, this would be 1. Are you getting it? I want you to grasp the idea. You don't have to write the 1 factorials, the ones that are repeated. So then again, please, 2 doesn't go into 4, you can't do that. Your answer is, please, 12 ways. Are you with me? Let's change, because the next question said, if I change the T into a S as well. Do you agree?
Yes, ma'am.
So we're playing around with the words, literally. So the number of arrangements
4.
is 4 factorial over
3 factorials.
1 factorial, 3 factorial. What does that give me? 4 ways. Can you see it? Either got it like it is there with the M in the front, or the M in second place, or the M in third place, or the M at the end. The S is everywhere else. Can you see it?
Yes, ma'am.
And if you could just see the answer and you told me 4, are you right? Yes, perfect. Unlike with, for instance, differentiation, calculus, where I told you you have to show me your notation, it's got to be perfect, you're going to get marks deducted if you don't. With probability, it's okay. Whatever you write, it's okay. They don't care about the ways of writing. Are you with me?
Yes, ma'am.
Okay, let's have a look at Bafana, but listen carefully to the question. Don't get so set in your ways, this is what I'm going to be doing. There's a principality. I gave you the word Bafana. It's again like your little brother or sister's little blocks, and they can arrange it in any way. And I'm asking, what is the probability that there will be an A in the first place and an A in the last place? So if that is the case, I'm actually looking at this circumstance. There's an A, and there's an A. I don't want to put the A there, because I want to say how many possible things will make me happy about this. So the A is there and it's done. It's fixed. Or is it 2 possibilities? Which A? Because there's actually 3. Shouldn't I say I've got 3 choices? No, because the A's are identical. So it doesn't matter which one goes where. Here's the 3 A's. Put this one there. Does it make a difference if I take another one and put it there?
No.
So there's one choice. Now, ma'am, who says it's going to be there? This is the scenario. I'm trying to find out what is the probability of this happening. So this is my request. There has to be an A in the front and there has to be an A in the back. So how many choices do I have, please? One. Are you with me? There's another A together with the other stuff. How many other things are there?
Wow.
There's 6 of them, right? 2, 4, 6, and I've already used 2. Okay, so what has happened here for the rest of them? How many ways can I arrange them? 4 factorial. But now this is the end of the event. I'm taking you way back to probability that says the probability of an event is the number of possible favorable outcomes and the number of the whole sample space. So focus. Probability is always about this formula, and it's even on your formula sheet. But now for this question to be answered, you're going to go back to MIST and I and D to tell me how many possible arrangements are there. Because that is your sample. I wrote it wrong, sorry. Is your NS. Are you with me? The number of possible arrangements. And that would be what? So let's get back to D and I and whatever. So the number of arrangements are 6
Factorial.
Factorial divided by, let's do it. 1,
3,
3,
1,
1.
1.
I'm done with it, right? I'm done with it. And this is 1 again, and I'm done with it because those 3 make up this one, but look identical. If you just wrote 6 factorial over 3 factorial, I'm quite happy with you because that's the only one that is repeating itself. Are you with me?
Yes, ma'am.
Which gives me then what answer, please?
112.
So that is the whole sample space, all of the things that can happen with the little blocks that my brothers got there because of the 3 of them that look identical. So whether I have one in the second place and switch it with another one in the second space, it's the same thing. That's why we do the division. So if you can go to here and immediately tell me that this is over 120, you got marks. This is the principle of probability.
Wow.
But I need to find out the end of the event. How many possible ways can this happen? Now he's talking about it. That's all of the possibilities because of the repetitions. But if I look at this one, and now we've started with a nice one because there were 3 A's. They are fixed. The other A can be wherever it likes. It can be next to it, in the middle, I don't care. But this is full factorial. If you wanted to say 4, 3, 2, 1, there's 4 possible ones that can go to the first place. Are you with me? So that the end of the event is actually 1 times. Do you see it? Or just 1 times 4 factorial. So many ways of writing it. But it's 4 factorial, which is what? 24. So that this will be 24. So the possible ways that this can happen, that there's an A in the front and the back, swapping them doesn't make a difference because they're the same. Swapping one of them with the A wherever it's in the middle doesn't make a difference. There are 24 ways of doing it and getting to this scenario. What's the chances? Not a lot. This answer is, answer please,
0.2.
or 1 over?
5.
Okay, excellent. So 1 over 5, 0.2 or? Is everybody with me? And I don't care in which way you want to give it to them. So if you wrote 24 over 120 and you wrote it in fraction form, I like it. Decimal form, I like it. Percentage form, just answer them. If they asked you for decimals, answer them in decimals, or whatever the case was that they wanted you to do it. Alright, this is nothing technical in mathematics, talking about rubber bands and restrictions. It's when I want to audit something and I've got restrictions of things being together. So, the question says I've got items, A, B, and C, and I want to arrange them in how many different ways? Please tell me the answer. 3 factorial. Everybody happy on that? Yes. But now comes the restriction. But A and B must be next to each other for whatever reason. Maybe it's 3 people, they have to be in the same picture, maybe it's a husband and wife conference, whatever, so they have to stand next to each other, something like that's going to happen. And I want to know how many ways can they now be done. So please, my technical assistants, come stand here with me. So I'm saying that there are 3 things there. So we have 3 items. But I'm saying these 2 are inseparable. They demand to be together. They have to be together. So, how many things are there if they are glued together? 2. There's only 2. So that means that I've got 2 factorial. No, ma'am. But what about, just leave your arms. Look. So this is another way. Are you with me?
Yes.
So the 2 of them can be ordered in 2 factorial way, which is 2, right? And the 3 of them, she can either be on that side or on this side. But how many things are there? Because this is now rubber band. Banded together, single there. How many things are there? There are 2. And 2 things can be ordered in 2 factorial ways. But in the rubber band, it can be like this. I'm not going to let you loosen. Or this. Which means how many ways again? 2 factorial. Thank you very much, my assistants. My lovely assistants. So therefore, the number of ways are, if you see the rubber band and see them always standing there with each other, there's not 2 things. There are 3 things. But I treat them like 2 because the 2 are stuck together for whatever reason. So that means there will be 2 factorial ways. But inside of one of them, where the rubber bands are, if you want to look at it like this and see it like this, they are stuck together with rubber bands. So this one can look like that, or the other way around. So there's 2 things, but then this one, and I just have the habit of always saying, first of all, how many things are there, grouped together, banded together? There are 2. But inside of this rubber banded one, there are 2, and they can also be placed in 2 factorial ways. And how much is that? Are you with me? You could see them, either the single one standing on the left, standing on the right, but that's just 2 ways. But then the girls, in whichever one of those cases, can stand to the front or swapped around. Then you see it being 4 ways.
Yes,
all right. Let's get to more difficult seeing if you get grasping this, because we cannot put 50 objects here. There are 50 objects. 7 of them, and I didn't tell you what objects they were, so I'm just saying 7 of them must be together, whether it's textbooks or whether it's ornaments or I don't know what. I want to place 7 of them have to be next to one another, and another 6 of them have to be next to each other. So you're seeing the rubber band, around 7 of them, and the rubber band around 6 of them. But how many groups of things are there then? So there's 50. No, because 6 of them are 1, and 7 of them are 1. How many is gone of the 50? 13. Are you all with me? So the rest is 37, right? So there's 37 singles, whatever. 37 singles, then 1 group of 6, 1 group of 7. So how many things are there? 39. So yes, there's 37, and that's what I want to see. There's 50, right? 7 of them go together, 6 of them go together. Then 13's missing. So the single ones are 37. But 37 plus the group of 6 and the group of 7 makes 39 things. Big groups and single ones, but it's 39 objects. Which I then have to also know that the group of 7 of them together can stand on how many ways? 7 factorial. And in which order must that be? Doesn't matter. Doesn't matter. So in how many ways will this happen that those 7 will be together? So now, if you do go to your calculator, it's going to be a huge number. Tell me.
7,40
What?
times 10 to the power 52.
Oh, what does that mean? A lot. Because back to grade 8 when you did scientific notation, this means that you've got to take this comma and time it out with 10's 52 spaces. I don't even know what that is then. Millions and billions and trillions and whatever. A lot. A lot of ways that this can happen. Alright, but that was my question. So do you think it's okay to leave it 39 factorial, 6 factorial, 7 factorial in whichever order? Perfect. Perfect. Next part of the question. What is the probability of this scenario happening here? Probability is always the number of favorable events. This is the number of favorable events. Favorable to me was I wanted those 6 together and I wanted those 7 together and the rest of them I don't care. That's my favorable outcome. But what is my NS, please? 50. That's with no restrictions. That's what can happen with no restrictions. That's your NS. So this answer of 39, 7, 6, and again I want to repeat, can be in any order. That's your favorable event, the one that has the 7 together and the 6 together, and those 7 can be mixed any which way and 6 can be mixed any which way. Over NS, which is then 50, factorial. Can you give me an answer? Because my logic is telling me the chances of this happening should be very slim. It's like winning the lotto.
2,43 times 10 to the power -12.
Which means that this comma should be moving. So you got 0, 0, 0, 0, 0, 0. It's very, very slim that I take 50 objects and they turn out like this, that those specific 6 ones and those specific 7 ones are together, whichever order doesn't matter, and it gives me a very slim, almost improbable chance that by chance this will happen. Alright, let's get into a sum where I'm saying I want to take a photo of 7 netball players, but for some or other reason, Michio and Bongi must not stand together. What is the probability of them not standing together? So first of all, those are again 2 things. I don't want them to be together, but I'm going to use the fact that if I do know what the answer is, what is not the answer? So if you take, for instance, an example, the probability of it raining today is, say, 40%. Then what is the probability of it not raining? 60%, because those are the 2 things that will make up the whole. All right. So if I say that the probability of them standing together, let's have the number of arrangements so that they do stand together is the sums that we're busy with. The number of arrangements so that they do stand together will mean, are there 7 girls? Nope, there are
6.
Count them. Count them. 1, 2, 3, 4, 5, 6. It's not girls, it's things. Okay? 6. But this can stand on 2 ways. So the number of arrangements for them standing together, but ma'am, I don't want them to stand together, but we're going to use the fact that if I know how many ways they can and how it's the probability of them not standing together, then not standing together is the rest of making up 100%. So the arrangements that they do stand together is we know now that there are 7 girls. You saw my fingers going haywire. That there are actually 6
things
because this is banded together. So we say 6 factorial. But the 2 girls can stand on 2 factorial ways. So that's the number of times that they will stand together. So if I say, what is the probability of them standing together? What would that be? It would be the NE, which is this one. Do you agree with me?
Yes.
Over the NS, which is what?
7.
Excellent. Well, it doesn't matter. There's no rules, there's no restrictions. If I just let them stand, there's 7 factorial ways that they can stand. So this is the answer for them standing together, the probability. Please give an answer. 2/7, I like it, because I can see it. Let me help you see it. 7 factorial. Let me help you see it. Does that make sense?
Yes.
7 factorial is 7
Times
6 factorial.
Okay.
Can you see it?
Yes, ma'am.
Did I write that now? 7 factorial. Can you see it?
Yes, ma'am.
7 factorial is 7 times 6 factorial. And then you can see it cancelling out, but the answer would be
7. 2 over 7.
2 over 7. Because remember, that's just 2 times 1.
Uh-huh.
So that would be the probability of those two girls standing together. But I don't want them to stand together. So if that's the probability of standing together, then the not standing together would be, and that's the ball game. If you just wrote 5 over 7, that's fine. So sometimes you need to say, I don't want them together, but what's the probability of having them together? Then you just take it away from 1. Does it make sense?
Yes, ma'am.
Okay. All right, our next question says, I have to choose a chairperson, a vice chairperson, a secretary, and a treasurer from 10 people. So now you're going to tell me, but ma'am, we've done this. Yes, we have. You've got to put your mind into when do we do what, because we haven't had blocks yet for a while today. So if I say I have to choose 1, 2, 3, 4 spots from 10 people, how do I do that?
4 blocks.
4 blocks, excellent. Do you have to show me the blocks?
No.
Humor me so that I know that you're on the right track. How many possible choices do I have?
2.
Who said I can't repeat?
No one.
Because you can't have.
Of course, you can't have the same person in the same position.
Oh.
So they didn't have to tell me that. Are you with me?
Yes, ma'am.
So there's 9 people left, 8 people left, 7 people left. Answer, please. What do I do with it?
Times.
How many? 5?
40.
A lot of ways that you can choose out of 10 people for guys for a committee. Okay, next one. Let's try and finish up with this one. I've got 4 different Latin books. I've got 5 different English books, and I've got 5 different French books. In how many ways can I arrange them in any order?
Add.
Are you adding them, right?
Yes.
So 4 and 5 and 3 is?
12.
Are you with me? That is the straightforward question. How many ways can you do something with 12 objects? Doesn't matter what order, that's fine. The second part of the question, if I want them all together, if I want the same languages together, what are you seeing? What are you seeing?
Probability.
Rubber bands.
Oh.
How many things are there?
3.
3. The French, Latin, the English. 3. So how many ways?
3.
3 factors.
Factorials.
3 factorial, I'm sorry. But then, that's not it.
You still have to.
Because in each of these rubber bands, there are
3.
4 of them.
Ah.
There are
5.
5 of them that can be arranged in 5 factorial ways. And there are 3 other ones here. Now you might get confused if you first wrote this and then you wrote the 3 at the back. Any order, it's fine. I like to first say how many things are there, and each of them has a certain amount of factorials that you can go. Are you getting this?
Yes, ma'am.
And so the answer would be, please?
103,680.
Can there be a comma now here? Comma ways of arranging, it's number of arrangements. Let's do one last one. I only want the Latin books to be together. What are you seeing? 1 rubber band. So how many separate things? Now I want you to please focus. So I only want the Latin books together. They were 4 of the 12 books. So how many things are here?
9.
Excellent. Not 12 minus 4. The 4 together make up 1. And there's 8 others. So there is 9. Are you with me? But the band of Latin books can be put. And the others? Well, I don't care. Go anywhere. They can be together, they don't have to be together. And the answer is, please,
8,709,120.
a lot more because I've got less restrictions than this. So it's a lot more. And even this one, if you wanted to write down the answer, it would be a huge amount, 12 factorial. But you can leave it in factorial way and you can give me the answer as well.